And we're back. Welcome from the weekend. Today we will be turning our attention to the control plane as it pertains to large groups of routers called autonomous systems. Before we begin, some administrative loose ends. Project number 4, which is a Wireshark experiment using TCP, will be due April 13th. That is a Monday, 11:59 and 59 seconds. Let me verify that. April 13th is a Monday. Okay, so it is a week from yesterday, the airing of this particular screencast. Please make sure you're looking at that right away. If you do not have active connectivity to do the experiment live, there is a link in the assignment. The PDF is up on the Blackboard, and from this link you can download an existing PCAP file that stores information from a live capture. So you're encouraged to do it live. If you don't have an active connection, please do it from the downloaded PCAP file. The link is on the assignment. Okay, so where we last left off, we talked about comparison of link state and distance vector routing algorithms, and we measured it in a number of different ways. We talked about the message complexity, speed of convergence, and also robustness. And so as far as link state routing is concerned, with message complexity, the number of nodes times number of edges is the number of messages sent. And so the larger your network, i.e. the number of nodes is bigger N, you're going to end up putting more traffic on the network. With distance vector routing, the exchange of these distance vectors is only local, meaning that it's between neighbors. So the convergence time is going to vary because it takes time for that information to wash its way across the network. So on one side of the network, a node or a router exchanges information with its neighbor. That node exchanges that information with its neighbor, and it washes across the network. So convergence time varies because it takes time to do that. Speed of convergence. Link state routing runs Dijkstra's algorithm, and it requires BGO n squared for this algorithm to run. So for each of the nodes, it looks at each of the neighboring nodes. So that's n many times for each of the nodes, and up to order of n neighbors for that node. And so that results in our BGO of n squared time, and that comes from, if you look at the description of the algorithm for Dijkstra's algorithm for link state routing, you have two concentric loops. Okay. It also requires some number of messages, which is proportional BGO n e, where n is the number of nodes again, e is the number of edges. Distance vector, the convergence time varies. You might have routing loops in that you update your distance vector, send it to your neighbor then triggers an update in their distance vector, they send to you, and then you trigger an update in yours, send back to them, and you can have these oscillations, these routing loops back and forth. There's also a so-called count to infinity problem, where you end up updating your distance vector one little piece at a time. As you get the advertisements, your edge weight or distance vector increases, and that causes an increase in your neighbor's distance vector, which causes an increase again in your distance vector, and you end up iterating back and forth through this exchange of distance vector. You end up increasing your distance vector estimate piece by piece, ends up continually adding, the so-called count to infinity problem. Now, robustness with link state, you can advertise the incorrect link cost, and each node only computes its own table. So while they only compute its own table, if you advertise incorrect link information, everyone else gets this broadcast, and therefore their understanding of the least cost path is now polluted. Distance vector, you can advertise an incorrect path cost, and so the result of that is you have bad information, and you then propagate this error or flawed information through the network when your distance vector advertisement washes across the network, or at least information from that. Okay, so let's continue on with the material for today's sitting. So Intra-AS, AS stands for Autonomous System Routing in the Internet, specifically OSPF, Open Shortest Path First. So in order to make things scalable, we first talked about routing, whether it's distance vector or link state routing. We have a network, and let me choose a pen color here. How about blue? Blue shows up really well. So we have a network, and this network consists of a number of routers. I'm not going to draw all the interconnects, But you can imagine as the number of routers grows in your network, well, you can't have an arbitrary number of nodes in your network because eventually the link state broadcasts are going to overwhelm the bandwidth available. And also, if you are doing distance vector, it's going to take a really long time for your distance vector to go to your neighbors and their neighbors and their neighbors and ultimately wash its way across the network. So this does not scale. And you can imagine if instead of like 20 or 100 routers on your network, if you had billions and billions, you can't conceivably do this practically. And so in order to make it scale, you need to find other units that you can form that aggregate together sets of routers together, and that's called an autonomous system, or AS. And so this autonomous system, not only is it a way of scaling by introducing hierarchy or subgroups, if you will, it's also a way of introducing so-called administrative autonomy. And so if you have a network, you think about this in your home network, you have full administrative control over what happens on that network. You control what happens in terms of the type of Ethernet cable, whether it's wireless or whether it's wired, how many machines, how they're going to do the routing, whether your NAT box is going to have sticky entries or not, all sorts of things. And so this idea of administrative autonomy means that each network administrator can control all the routing information that swirls around his or her network. And so here, instead of having, say, and I'll draw this out, 1 billion routers together in a network, well, we can aggregate them. We can say, okay, this group of routers, that's one particular administrative control domain, and this group is another administrative control, and this group is another administrative control, and that group is another administrative control. Now, as such, each one of these is going to run a routing algorithm, so I'll just say algorithm that could run link state, and maybe this one will run distance vector, maybe this one will run a different type of distance vector, and maybe this will run a different type of link state algorithm. So that's link state algorithm 2, distance vector algorithm 2, that might be distance vector algorithm 1, that might be link state algorithm 1. And so with this administrative control associated with some aggregation or group of routers, you can decide as an organization what suits your network best while still interacting across the internet. Now, certainly to interact across the internet, you want to have this group share a link with that group, and it's a bidirectional link. Likewise, this group shares a link to that one, and that one will also maybe share a link here and share a link here. Okay? And so this is called an autonomous system, or AS, and we will talk about how routing happens both within an autonomous system, so from this router to this router to this router to this router to this router, as well as between autonomous systems, from this particular router in this first AS to that particular router in the other autonomous system. Okay, so we can aggregate routers into regions, and these regions are known as autonomous systems, ASs, and sometimes you call them domain. And as such, you need two pieces of information, two things to happen. So let's assume we have autonomous system 1, and that has a set of routers that can route between one another, okay? And then we have another autonomous system, AS2. Now, it just so happens, all right, well, as autonomous systems, they know how to advertise distance vectors and path costs and find optimal routes and all that good stuff. So you need a way to route between routers in the same autonomous system if you're going to use this approach to group them together in order to make it scalable. And then you'll also need a way to get packets between autonomous systems, say this router here in AS1 and that router in AS2. Now, within an autonomous system, it's as we had learned or as we had discussed when we talked about link state routing and distance vector routing. And this is so-called Intra-AS routing. And Intra-AS routing concerns the routing among hosts and routers in the same network, or in this case, the same autonomous system. And all routers in the same autonomous system, this is a requirement, they must or they have to run the same intra-domain protocol. So if this AS is running link state routing, that means all of the routers in the autonomous system, this first one, must run that same link state routing algorithm. Likewise, if this autonomous system is running distance vector routing, all of the routers in this autonomous system or in this network must also run the same distance vector routing algorithm. So routers in different autonomous systems, therefore, can run different intra-domain routing protocols or algorithms. And what this means is that this intra-domain routing or intra-AS routing protocol is responsible for pushing data or information concerning routes to every single router in that particular network or that autonomous system. Okay, so now we also need, if we're going to have this aggregation, we need another type of routing algorithm, and this is the so-called Inter-AS routing algorithm. And that's responsible for propagating distance vector information or path advertisements to routers in another autonomous system. And what we'll see is we'll designate certain routers within each autonomous system as a so-called gateway. And what a gateway is, it's a router in your autonomous system that, while it maintains a connection to all of the routers inside the autonomous system, it also maintains a connection to a router that's in a different autonomous system. Okay, so let's take a look at an example. Here we have a set of interconnected autonomous systems. We have the first one, AS1, down below. We have the second one, AS2, on the right, your right. And we have the third one, AS3, on the left, your left. Now, within each one of these autonomous systems, we have three routers. So in AS1, we have 1A, 1B, 1C, and 1D. Those are all routers in the first autonomous system. We have routers 2A, 2B, 2C. Those are routers in the second autonomous system, AS2. And then lastly, we have 3A, 3B, 3C that are in AS3. Now, if we look at each one of the forwarding tables, we said forwarding tables are configured by the routing algorithms. But in this particular case, the forwarding table is going to be influenced by two different routing algorithms. Those are the Intra-AS routing algorithm and the Inter. Let me say that again. Those are the intra-routing algorithms and the Inter-AS routing algorithms. And so the Intra-AS routing algorithm is going to determine forwarding table entries corresponding to destinations on subnets that are in the same network. And so the intra-routing AS algorithm for, say, Autonomous System 1 is going to determine forwarding ports associated with blocks of addresses, subnets, managed by router 1A, 1B, 1C, and 1D. Anytime you want to go to a block of address or subnet that's not in Autonomous System 1, well, that's going to be set, those forwarding table entries are going to be set by the Inter-AS routing algorithm. And so this forwarding table can get its entries that talk about, for a given subnet, out which port you're going to forward your datagram. It's going to get its entries from two different sources, those representing addresses that are within the autonomous system and those corresponding to subnets that are outside of the autonomous system. Okay, and so together these two work in concert to give you all of your forwarding table entries regardless of the autonomous system where that network address might exist or that subnet might exist. Okay, so let's look at the task for Inter-AS routing. So suppose we have a router in Autonomous System 1 and it's going to receive a datagram, and this datagram that it receives is destined to go outside of Autonomous System AS1. So this router then, if this datagram that it gets should go to another autonomous system, so its destination is not in AS1, AS1 needs to know which router at the boundaries or the borders, if you will, its gateways, which gateway should it push this datagram to. And the gateway that it should push the datagram to is the gateway that has on the other side of its link a router that manages addresses or subnets corresponding to the destination address on that datagram. So Autonomous System 1 has to learn two things: which destinations are reachable through AS2, so what subnets are available in this direction, and which destination addresses or subnets are available through AS3. That is, in this direction, what subnets are managed by routers within AS3. Now, once it knows what those subnets are, well, the corresponding gateways in AS1 now have to propagate that information to all of the routers within the autonomous system. And so the determination of that block of addresses in a different autonomous system, that's where the Intra-AS routing algorithm comes into play. And then the pushing of that information to all of the routers within the autonomous system, that's where the Intra-AS routing algorithm comes into play. Okay, so that pushing or propagating of information, reachability information, or subnets for a particular port or a foreign autonomous system is the job of the Intra-AS routing algorithm, pushing this information to all of the routers in the same AS. Okay? All right. So this is called sometimes an interior gateway protocol. And the most common intra-AS routing protocol are RIP, Router Information Protocol, and this is fairly old. That's a form of link state routing. OSPF, Open Shortest Path First, that's also a form of link state routing. And something called Interior Gateway Protocol, which used to be proprietary to Cisco, but it was made a public standard relatively recently. That's a form of distance vector routing. And so OSPF is also link state just like RIP, but it adds an improvement on RIP, the ability to hierarchically aggregate large groups of routers into something called areas. Okay, so let's continue. So Open Shortest Path First, or OSPF, it's publicly available. It uses link state routing, and it disseminates so-called link topology information, all of the edge weights, using a flooding approach. And so this packet dissemination, link state packet dissemination, is used to get all of that traffic information from each node, the so-called link state broadcast, to every other node on the network, every other router. And so the route computation itself, once every node has the complete set of edge information, it's used, that's a route, is calculated using Dijkstra's algorithm, exactly the same algorithm that we had studied. And so it uses flooding, per se, to accomplish this dissemination of all of the link state to all the nodes in the network. And by flooding, what I mean is that you have a bunch of routers, and if this router is flooding, it sends its link state to each one of its neighbors. And when a node gets link state information, it sends a copy of that to each one of its neighbors, right? And so in doing so, eventually all of the link state information is delivered to every single node on the network. Okay. And so flooding is used in OSPF to push advertisements to all the routers, i.e. to propagate all of this topology information associated with all of the path or all of the link costs to every router in the network. Okay. And so the IS-IS routing protocol is another variant. It's identical to OSPF. So OSPF adds security. Now, of course, it's a dangerous thing. If you're a router, someone could advertise paths and then not even a real router, somebody who wants to intercept data, save it, and then try to maybe crack something later on. And so OSPF also adds the ability to authenticate routers. So you configure a bunch of routers on the network. They can authenticate one another and say, yes, you are an honest-to-goodness, legitimate router on the network. And so you can have multiple same cost paths in OSPF. In Dijkstra, we talked about the scheme for breaking ties, but in OSPF, it allows you to have more than one path that has the same cost. Okay. Now, for each link that you have, you can have different costs associated with the same link depending on the type of service. So, for example, if you have router A and you have router B and you have router C, for example, well, for different types of service, you can say for one type of service where the TOS field is marked in the datagram, this is going to have a cost of 7. But for another type of service, it's going to have a different cost. And that's almost like having a different version of the link that I'll draw in dotted line format. And maybe that different version of the link is going to have a cost of 10. So in that particular case, let's make that 3. And let's make that, I don't know, let's make that 10. Okay. So in some cases, maybe you want different path costs depending on some marking that you can associate with the datagrams. So for example, if you want a best effort network, meaning that it's going to try to send things as quickly as possible using as much bandwidth as possible, and for best effort, a satellite link would have a low cost associated, meaning that it would prefer to have a lot more traffic sent over that link. If you want real-time marking for your type of service, well, real-time means you want the upper bound on the time for delivery across that link to be relatively small. Now, since satellites take a long time, then you'd increase the cost of the satellite link if you're interested in real-time performance for your end-to-end flow. And so OSPF allows you to differentiate the path that's taken based on things you can mark in your datagram. You also have support for so-called multicast and unicast. With multicast, you use the same topology data, i.e. all of the link weights or edge weights in your network graph. But with multicast, you can set up what's called a spanning tree. And this spanning tree is a subtree that maintains connectivity among all the nodes such that you can now send one message once from one node and it'll get delivered automatically to all the nodes on this so-called spanning tree for this multicast. You can also do this hierarchical arrangement in OSPF so that an autonomous system with a large number of routers on the network can be subdivided into what are called areas. You can think of them as mini autonomous systems that are collected together within a single autonomous system. So let's take a look at hierarchical OSPF. Now, in this particular version of hierarchical OSPF, we're using a tree-like structure, but it doesn't have to be a tree-like structure. This is just a good way of demonstrating some of the features of hierarchical OSPF. So here we have a single area, right? A single autonomous system. That single autonomous system is the entire group of routers, and that entire group of routers is collected together, and the administrative responsibility is owned by one set of network administrators. So that's an autonomous system. Now, because you can have a lot of routers in an autonomous system, one way you can get scalability when you have a lot of things is to aggregate them hierarchically. And so OSPF allows you to do this hierarchical aggregation. And so you take all the routers that you have and you divide them into subgroups within the autonomous system. And these subgroups are called areas. And in this example, you have 3 areas. You have area 1, you have area 2, and you have area 3. Now, there are routers in an area, and they're running link state routing, distance vector routing, what have you. And each of these areas are then stitched together by other routers whose responsibility is to get those datagrams from the routers within an area, so-called internal routers, those are routers within an area, to other internal routers or to the gateway associated with that autonomous system. And the gateway is at the quote-unquote border, at the edges. It borders other autonomous systems. So imagine you have another autonomous system here. Well, this router is the border gateway. It's at the border between our autonomous system, that's ours, and the other autonomous system, let's call it theirs. Okay? And so this router at the border, that hasn't changed, but in hierarchical OSPF, it's given a different name. It's called the boundary router. And this boundary router sits at the border and is responsible as that last point from which datagrams will enter or leave our autonomous system. Okay? So a boundary router is nothing more than a border router or border gateway or gateway. Okay? So we have areas. These are aggregation subgroups of routers within an autonomous system. The routers inside of an area are called internal routers, We have this boundary router, which is the gateway at the border that connects you to other autonomous systems. And then we have those routers on the so-called backbone. The backbone routers are those responsible for aggregating all that traffic from an area to ultimately either get to another area, like that edge, or to the boundary to get off the network and in the reverse direction on to the network. So we have these backbone routers, and then each area, each subgroup within the autonomous system in this hierarchical OSPF, each area has a special router called an area border. And that area border, it acts like a gateway for the area, right? It's not a gateway for the entire autonomous system. It's just a gateway for that subgroup within the autonomous system. So this area border routers, they connect each area to the backbone to form this hierarchy of autonomous, collectively, that forms our autonomous system. So I could add another area. I could say, okay, well, let me include another backbone router, and I'm going to add a link from that level of the backbone hierarchy. And now I'm going to push that out to another area. Let me call that area 4. And area 4 is going to have some number of routers, and they're going to be interconnected. And that area is also going to have its border router, and that area border is going to connect area 4 to the backbone through some router, or maybe through an existing backbone router. So this so-called hierarchical OSPF allows you then to save money as well as scale your network. And so certainly these area border routers aren't going to deal with as much traffic because they're dealing with traffic from one of the areas, which is a smaller subset of the total routers that are in the autonomous system. Now, these backbones, they're going to deal in more traffic because they're aggregating multiple areas together. And then finally, this boundary is going to be very high performance because it's dealing with all the traffic, both outbound and inbound, for all of the subnets managed by our autonomous system. Okay. So in this two-level hierarchy, we have the local area, we have the backbone, and we have link state advertisements, because OSPF is link state routing. Link state advertisements only remain within an area. So that actually makes sense, because if you have a large number of routers in the autonomous system, by limiting the link state broadcast only to routers within an area, you're cutting down on the amount of traffic that's swirling around the network. So you're localizing that traffic within an area. And so each node has an area topology, and then each node within an area knows the detailed link cost information, because those link state broadcasts are limited only within an area. They also know the direction or the shortest path to get to networks in other areas. And so each node knows all of the link information within the area. So say area 1 here, they know all the link information within the area. But then they also know that if I want to get a datagram to a subnet managed by area 2 or managed by area 3, I know I'm going to have to get my message to that area border, ultimately out of this link. Okay, so the backbone routers also run OSPF, but this OSPF routing broadcast information is only among routers in the backbone. Now, what is in the backbone? Well, the backbone routers are in the backbone, but the area border routers also maintain connections within the backbone. And so you're also going to run OSPF within the backbone. There's two separate groups of routers running link state. And so these will broadcast link state information to one another, keeping them within the backbone. Now, that's going to be different link state broadcasts from what's happening within each of these areas. So those two sources of traffic are partitioned from one another. Okay, so the backbone routers run OSPF routing, so that's link state broadcast through flooding, as well as Dijkstra's algorithm, but it limits it to the backbone. And the boundary routers, as I said, connects to other autonomous systems. That's the boundary out here for all of the outbound traffic from our autonomous system to someone else's autonomous system. Okay, so let's take a look at the inter-autonomous system routing. We just said something about intra within autonomous system, and OSPF allows us to authenticate and also allows us to aggregate things hierarchically within an AS using areas. Okay, we stitch together those areas using backbone routers, and those areas can get data to and from one another using these area border routers. Okay, so let's take a look at how you get routing datagrams routed between autonomous systems. And so the de facto protocol for routing inter-domain between different autonomous systems is called BGP, or Border Gateway Protocol. And Border Gateway Protocol is the glue that stitches together the internet. That's the reason why you, if you're a Verizon customer, you're able to send a message to somebody who is a Sprint customer. It's because of BGP that you can do that. So BGP provides two types of messages, and these messages provide reachability information that says, if you want to get to this block of addresses, this subnet, you need to go through me. I manage that. And ultimately that boils down to being forwarded out the correct link, output port. Okay, so those two messages are the following. One is an eBGP message that's for external Border Gateway Protocol. And this eBGP message obtains reachability information for a subnet for neighboring autonomous systems. So that's for external autonomous systems. Now, iBGP, I stands for internal Border Gateway Protocol messages. These messages are used to propagate reachability information, i.e., who manages this subnet or block of addresses. It gets this information to all of the routers within an autonomous system. And so the idea then is to determine what are quote-unquote good routes to get to other networks based on reachability information, which we've always done, but also policy. Now, this policy is pretty wonky, right? It's because it's not just reachability you're concerned about, the least cost path. What you're also worried about is what sort of financial agreements or partnerships you've engaged in. Now, if you are not engaged in a partnership with, say, Verizon, you might say, well, I don't want Verizon traffic coming through my network if it's trying to get to Sprint. So this policy, in addition to this least path cost, i.e. reachability information, is used with Border Gateway Protocol. And we'll explain a little bit more about what that means. And so what these messages are, you can think of them as advertisements. They propagate to neighboring routers along the link to say, hey, if you want to get to this subnet, I have a path to get there. So it allows the subnet to advertise its existence to the rest of the internet, to say, I am here. I manage these addresses, these blocks of addresses, these subnets. Okay, so let's take a look at this. So here we have three autonomous systems, AS1 to the left, AS2 in the center, and AS3 on the right-hand side. Now here, within an autonomous system, we'll focus our attention on AS2 in the center. We notice we have this blue dotted line between all the routers in AS2. We have router 2A, 2B, 2C, and 2D in autonomous system AS2. Now these blue edges are intra-AS links, which represents the connectivity between routers within AS2. These correspond to iBGP connections. And so that means each one of these routers in AS2, router 2A, 2B, 2C, and 2D, have connections directly to one another in order to propagate reachability information about subnets managed by routers within AS2. Then we also have these red edges, and you'll notice these red edges are between routers at the border, the so-called border gateways. And these border gateways' responsibility is to push data to the border gateway on the other side of the link, and that border gateway at the other side of the link is in a different autonomous system. And so it's these border gateways that are responsible for getting your datagram from AS2, for example, to AS1, or from AS1 to some router managing a subnet in AS2. And so here we have an eBGP connection, that's this red dotted line, between border gateway 1C, which is in AS1, and border gateway 2A, which is in AS2. Likewise, we have one of these eBGP connections between border gateway 2C in AS2 and border gateway 3A in AS3. Okay, so the gateway routers are going to run two routing protocols. It's going to run the iBGP routing protocol so that it can propagate reachability information to all of the routers within its autonomous system. And it's also going to run eBGP routing protocols in order to propagate connectivity information across its borders to the border gateway in another or in a different autonomous system. And so these two things working together are important so that every router within an autonomous system will be able to identify where a datagram needs to go if the message, regardless of if the message or the datagram is destined for a subnet in the same autonomous system or subnet in a different autonomous system. Okay, so let's say we have a BGP session and we have two BGP routers, we call them peers, and they're exchanging BGP messages over a TCP connection. Now, this TCP connection is generally a persistent connection. They leave them open because they're going to exchange this information, these eBGP and iBGP messages frequently across their connections. And so what happens in this BGP session? They're going to advertise paths to different network prefixes, i.e. a subnet. So you can think of a network prefix as a subnet, and what it has is a path vector. So it tells you what autonomous system it belonged to and what is the subnet. Okay, so here's an example where we have some router in Autonomous System 3, and this router manages subnet address X. We'll just call it X. It doesn't matter what it is. And so Autonomous System 3's gateway router, 3A, that it shares on the border with Autonomous System 2's 2C border router, it's going to advertise sending an eBGP message that says, hey, I'm Autonomous System 3, and if you want to get to subnet X, I manage that. And so 2C in Autonomous System 2 is going to get this message, and it knows if there's any subnet address X, it's going to go to Autonomous System 3, and I would do it through this link. Okay, so in doing so, when 3A in Autonomous System 3 sends this, it promises to AS2 that if you send me any datagram stamped with subnet address X, it will forward those datagrams in the direction towards X. It'll get it there for you. Okay, so let's say router 2A then had a datagram that was stamped with subnet address X. Well, once 2C gets this advertisement from AS3's border gateway 3A, it's going to use iBGP to propagate that advertisement to all of the routers in its autonomous system and says, hey, if you want to get to subnet address X, come through me. So now 2B knows if I want to go to X, I'm going to go in this path. 2D knows I'm going to go in that path, and 2A knows I'm going to go in that path. Okay, so all of those routers then in Autonomous System 2 are going to know where to go, where to send a datagram stamped with X, because 2C has gotten that advertisement from AS3, and 2C has propagated that eBGP message locally using iBGP. Okay? All right. So, what does this advertisement consist of? Well, it has a prefix and it has certain attributes. And these prefix plus attributes consist of the route. Now, there are two important attributes associated with this advertisement. One is the AS path, so it's the list of autonomous systems through which this advertisement has passed. So you kind of log down or note down in this advertisement which autonomous systems it will traverse, and then also the next hop. And that next hop is specifically internal to the autonomous system, the router to the next hop AS. So in this example, well, it says AS3X, and the next hop router for autonomous system 2, that's going to be 2C. That's the next hop router, because every router in autonomous system AS2 is going to use 2C as the next hop to get to autonomous system 3. Okay, so those two pieces of information are really, really important. This next hop is a specific internal AS router for the next hop to get to the next hop autonomous system. Then there's also this policy-based routing that I alluded to earlier. And what this policy-based routing does is it determines what advertisements you're going to accept on the inbound side. So let's say this is AS2, and you have its gateway, and then you have AS3, and you have its gateway. And so advertisements can go in two directions. And what this policy-based routing says, will I accept incoming advertisements from the perspective of AS2, and which advertisements am I going to allow to go out? And so in doing so, with the incoming, AS2 will refuse to propagate, AS2's gateway will refuse to propagate that advertisement coming from AS3. Likewise, with AS2, it will refuse or can refuse, based on policy, to propagate messages that say, hey, I manage a certain block of addresses. It can refuse to propagate those advertisements to AS3. And so policy-based routing says that a gateway can either import an advertised route, or it can export or refuse to export an advertised route. So the gateway receiving route advertisements uses a so-called import policy to either accept or decline advertisements on the inbound side. So that's the import policy. Okay. And the policy also determines whether or not it's going to advertise a path. So this is the advertisement of the path. You could call it, if you wanted to, an export policy. If it does not import, well, all of the routers in AS2 will not use this gateway to go across this link to send data to AS3. If it's a policy on export, well, it will not advertise to AS3, so AS3 will not push traffic through AS2 to get to some destination. So let's take a look at this with an example. We have three autonomous systems. We have AS1 to the left, AS2 in the center, and we have AS3 on the right. Now, AS3, we're going to use the same example. AS3 has a router, and that router manages subnet addresses marked subnet X. Okay, so now AS3 can advertise through its gateway that it shares on the border with AS2 through gateway 3A. It can advertise, okay, well, it marks the autonomous system AS3, and it manages subnet address X. Absolutely it does, because there's a router in AS3 that manages subnet address X. So if you want to send data to subnet address X, well, you're going to go through this gateway 3A to get there. Okay, so now AS2's router 2C receives the path advertisement AS3, that's the autonomous system, and here is the subnet address. And it gets it as an eBGP message along this red link between border gateways, hence the name Border Gateway Protocol. So it gets this eBGP message from AS3, and this source of this message is router 3A in AS3, and the destination is border gateway or router 2C within AS2. So AS2 router 2C receives a path advertisement from AS3 router 3A. Now, based on the policy for AS2, it can either accept this path advertisement from 3A and AS3 and propagate it using iBGP to all of the routers in AS2. Now, if it accepts this advertisement and propagates using iBGP, now that means each one of these routers, 2A, 2B, and 2D, will know if I want to send to subnet address X, I'm going to go through router 2C, which is going to go across this link to 3A. Now, this information gets propagated internally using the intra-BGP message, iBGP. Okay. Now, based on AS2's policy, it can choose to export this advertisement that it got from AS3. Now, of course, router 2A through iBGP, it got that message that if you want to go to AS3, you're going to go through this gateway router, which has a connection to 3A. Now, 2A has this message, AS3, this advertisement, subnet X. And now, this gateway router 2A can send out an advertisement. When it sends out the advertisement, it adds AS2 as one of the autonomous systems that this advertisement has traversed. So it's going to say AS2, AS3, subnet address X. Okay. So now AS2's border gateway 2A is going to send out an advertisement based on policy. The policy could be, don't send it. I don't want AS1 to know that I know how to get to router X in AS3. If it says by policy that I will accept traffic from AS1, then I'm going to send this advertisement. So based on the policy for Autonomous System 2, AS2's border gateway that it shares with AS1, that router 2A, a border gateway, will advertise using eBGP, External Border Gateway Protocol, message across the red link, that the path AS2 to AS3 that manages subnet address X. And it sends it to border gateway router 1C. So AS2 shares a border using router 2A to router 1C. And now router 1C in kind will send iBGP messages, to each one of the routers it has. And this iBGP message it sends to every router inside of AS1 will say AS2 is a hop, AS2 to AS3. That's the other hop for address X. Okay. And then AS1 will advertise that out its border gateway to whichever autonomous system is connected to that border gateway. All right. So, as such, a gateway router at the border can learn about multiple pathways to get to a destination. And in this example here, AS3 shares a border with AS2 through router 2C and router 3A, that eBGP connection. AS2 shares a border with AS1 through the connection between border gateway 2A and 1C. Likewise, AS3 shares a connection at the border between AS1 through an eBGP connection between border gateway 3A and 1C. So there are two different ways we can get a message from Autonomous System 1 to subnet address X. We can go directly across this link through that edge directly to the border gateway that AS1 shares with AS3, or we can go through the border that AS1 shares with AS2, and then through the border that AS2 shares with AS3. So there are multiple paths that we can learn about. Now, AS3, again, is going to send a path advertisement, AS3, through eBGP for subnet X, that gets propagated among all the routers in AS2 from 2C using iBGP messages, and then it gets advertised across the border, adding the autonomous system 2 as the next hop. So it propagates using eBGP messages, this red edge, across its border that AS2 shares with AS1, and that message is AS2, AS3, X. So from the perspective of border gateway 1C on the border of AS1, it gets that message, AS2, AS3 for subnet X, from AS2. Okay. Now the other message that it gets through eBGP is through that direct border that AS1 shares with AS3. So router 3A sends an eBGP message across that link it shares with the border of AS1, and it has that autonomous system, that hop, if you will, and it has subnet X. So AS1 gets that other message, and that message happens to be AS3 for subnet X. So now anytime you want to send a datagram from some subnet in AS1 to an address X subnet in AS3, you have two choices. Are you going to go across the border that AS1 shares with AS3, or are you going to go across the border that AS1 shares with AS2 indirectly, and then across the border between AS2 and AS3 to get to that destination subnet X? So AS1 gateway router 1C learns the path AS2 hop to AS3 for subnet X from 2A, and it learns at the same time path AS3 hop directly for subnet X from 3A. Okay, so let's say based on policy, AS1's gateway router 1C chooses the path directly to get to AS3, and it advertises a path within AS1 via iBGP. So that means if it selects this direct border with AS3, it'll send this AS3X message to each one of the routers propagate within the autonomous system using iBGP. So that means now every router that manages a subnet, if it gets a datagram and that destination address is X, it's going to forward it to this border gateway, and it's going to go out this edge to get to 3A in order to forward to subnet address X. Okay. So this is all based on policy, and it could be based on policy. Maybe there's a sharing agreement between Autonomous System 1 and Autonomous System 3. So let's put some names on this. Maybe this is Verizon. Maybe this is Sprint. And maybe this is T-Mobile. And let's say you want to send a datagram from your machine on Verizon to Sprint. And if there's no sharing agreement for data between Verizon and T-Mobile, it's going to choose that path. So that means that the forwarding intra-autonomous system is going to accept advertisements from across the border, but only allow or only accept those from AS3 and not from AS2. And that's how it prefers this path directly across the border between AS1 and AS3. Okay, so BGP messages are exchanged between so-called peers. And these peers can be peer routers because they act like peers in the peer-to-peer sense. Now, when they act like clients, they send. When they act like servers, they receive a message. And so these peers are border gateways in other autonomous systems. So if we have AS2 here and we have AS1 here, well, that router at the border that it shares with AS2, these two routers are peers. So you can send and receive, act like a client and act like a server. You can send and you can receive, act like a client and act like a server. So these BGP messages, there are a bunch of different messages. One's called open. It initiates a persistent TCP connection to some other peer or router, and it authenticates that sending BGP peer. And that authentication is really, really important, because if you are establishing a connection with a border gateway for a different autonomous system, you want to make darn sure that this is actually the border gateway for the second autonomous system. And you can use certificates and standard cryptographic methods to do that. You also get update messages. So there's the open to establish a connection. There's the update to advertise a new path or withdraw an old path. There's keep alive, maintain that connection. And there are also notifications if there were errors for error reporting. Okay, so with that, we'll move on next to the SDN control plane. And this is a very good stopping point to stop, and we will continue on next time in this conversation with the control plane in a software-defined networking scenario. So with that, I will see you all on Thursday.